Learning objectives. In this chapter, the user would learn the following in detail: frequency domain sampling, properties of DFT, linear filtering method based on DFT, frequency analysis of signals using DFT, FFT algorithm, applications of FFT, Goetzel algorithm, quantization effects in the computation of DFT. Applications of FFT algorithms. The FFT algorithm is used as an efficient means to compute the DFT and the IDFT. In this section, we consider the use of the FFT algorithm in linear filtering and in the computation of the cross correlation of two sequences. In addition, we illustrate how to enhance the efficiency of the FFT algorithm by forming complex valued sequences from real valued sequences prior to the computation of the DFT. Efficient computation of the DFT of two real sequences. The FFT algorithm is designed to perform complex multiplications and additions even though the input data may be real valued. The phase factors are complex and hence after the first stage of the algorithm, all variables are complex valued. Suppose that x1 of n and x2 of n are two real valued sequences of length n, and let x of n be a complex valued sequence defined as x of n equal to x1 of n plus j x2 of n, 0 less than or equal to n less than or equal to n minus 1. The DFT operation is linear and hence the DFT of x of n can be expressed as x of k equal to x1 of k plus j into x2 of k. The sequences x1 of n and x2 of n can be expressed in terms of x of n as follows: x1 of n equal to x of n plus x star of n by 2, x2 of n equal to x of n minus x star of n divided by 2j. Hence, the DFTs of x1 of n and x2 of n are x1 of k equal to 1 by 2 times of DFT of x of n plus DFT of x star of n, x2 of k equal to 1 by 2j DFT of x of n minus DFT of x star of n. Recall that the DFT of x star of n is x star of n minus k. Therefore, x1 of k equal to 1 by 2 times of x of k plus x star of n minus k, x2 of k equal to 1 by j square x of k minus x star of n minus k. Efficient computation of the DFT of a 2n point real sequence. Suppose that g of n is a real valued sequence of 2n points. We now demonstrate how to obtain the 2n point DFT of g of n from computation of 1 point DFT involving complex valued data. First, we define x1 of n equal to g of 2n, x2 of n equal to g of 2n plus 1. Thus, we have subdivided the 2n point real sequence into n point real sequences. Let x of n be the n point complex valued sequence, x of n equal to x1 of n plus j into x2 of n. From the results of the preceding section, we have x1 of k equal to 1 by 2 times of x of k plus x star of n minus k, x2 of k equal to 1 by 2j times of x of k minus x star of n minus k. Finally, we first express the 2n point DFT in terms of the 2n point DFTs x1 of k and x2 of k. To accomplish this, we proceed as in the decimation in time FFT algorithm, namely g of k equal to summation n equal to 0 to n minus 1 g of 2n into w 2n power 2nk plus summation n equal to 0 to n minus 1 g of 2n plus 1 into w 2n power 2n plus 1 of k equal to summation n equal to 0 to n minus 1 x1 of n into wn power nk plus w 2n power k into summation n equal to 0 to n minus 1 x2 of n into wn power nk. Consequently, g of k equal to x1 of k plus w2 power k n x2 of k, where k equal to 0, 1, etc. n minus 1, g of k plus n equal to x1 of k minus w2 power k n x2 of k. Thus, we have computed the DFT of a 2n point real sequence from 1 point DFT and some additional computation. Use of the FFT algorithm in real filtering and correlation. An important application of the FFT algorithm is in FIR linear filtering of long data sequences. Earlier we described two methods, the overlap add and the overlap save methods for filtering a long data sequence with an FIR filter based on the use of the DFT. In this section, we consider the use of these two methods in conjunction with the FFT algorithm for computing the DFT and the IDFT. Let h of n 0 less than or equal to n less than or equal to m minus 1 be the unit sample response of the FFT filter, and let x of n denote the input data sequence. The block size of the FFT algorithm is n, where n equal to l plus m minus 1. And l is the number of new data samples being processed. Samples is selected so that n is a power of 2. For purposes of this discussion, we consider only radix 2 FFT algorithms. The n point DFT of h of n, which is padded by l minus 1 zeros, is denoted as h of k. The computation is performed once via the FFT and the resulting n complex numbers are stored. The decimation in frequency FFT algorithm is used to compute h of k. This yields h of k in bit reversed order, which is the way it is stored in memory. In the overlap save method, the first m-1 data points of each data block or the last m-1 data points of the previous data block. Each data block contains l new data points such that n equal to l plus m minus 1. The endpoint DFT of each data block is performed by the FFT algorithm. If the decimation in frequency algorithm is employed, the input data block requires no shuffling and the values of the DFT occur in bit reversed order. Since this is exactly the order of h of k, we can multiply the DFT of the data, say xm of k with h of k, and thus the result ym of k equal to h of k into xm of k is also in bit reversed order. The inverse DFT, IDFT, can be computed by use of an FFT algorithm that takes the input in bit reversed order and produces an output in normal order. Thus, there is no need to shuffle any block of data either in computing the DFT or the IDFT. If the overlap add method is used to perform the linear filtering, the computational method using the FFT algorithm is basically the same. The only difference is that the endpoint data blocks consist of l new data points and m-1 additional zeros. After the IDFT is computed, for each data block, the endpoint filtered blocks are overlapped and the m-1 overlapping data points between successive output records are added together. Let us assume the computational complexity of the FFT method for linear filtering. For this purpose, the one-time computation of h of k is insignificant and can be ignored. Each FFT requires n by 2 log 2n complex multiplications and n log 2n additions. There are also n complex multiplications and n-1 additions required to compute ym of k. Therefore, we have n log 2n by l complex multiplications per output data point and approximately 2n log 2n by l additions per output data point. The overlap add method required an incremental increase of m-1 by l in the number of additions. By way of comparison, a direct form realization of the FIR filter involves m real multiplications per output point if the filter is not linear phase and m by 2 if it is linear phase symmetric. Also, the number of additions is m-1 per output point. It is interesting to compare the efficiency of the FFT algorithm with the direct form realization of the FIR filter. Let us focus on the number of multiplications which are more time consuming than additions. Suppose that m equal to 128 equal to 2% and n equal to 2 power v. Then the number of complex multiplications per output point for an FFT size of n equal to 2 power v is C of v equal to n into log 2 to n divided by L equal to 2 power v of v plus 1 divided by n minus m plus 1 approximately equal to 2 power v of v plus 1 divided by 2 power v minus 2 power 7. The values of C of v for different values of v are given in table 6.3. We observe that there is an optimum value of v which minimizes C of v for the FIR filter of size m equal to 128. The optimum occurs at v equal to 10. C of v represents the number of complex multiplications for the FFT based method. The number of real multiplications is 4 times this number. However, even if the FIR filter has linear phase, the number of computations per output point is still less with the FFT based method. Furthermore, the efficiency of the FFT method can be improved by computing the DFT of 2 successive data blocks simultaneously according to the method just described. Consequently, the FFT based method is indeed superior from a computational point of view when the filter length is relatively large. Table: computational complexity. The computation of the cross correlation between two sequences by means of the FFT algorithm is similar to the linear FIR filtering problem just described. In practical applications involving cross correlation, at least one of the sequences has finite duration and is akin to the impulse response of the FIR filter. The second sequence may be a long sequence which contains the desired sequence corrupted by additive noise. Hence, the second sequence is akin to the input to the FIR filter. By time reversing the first sequence and computing its DFT, we have reduced the cross correlation to an equivalent convolution problem, that is, a linear FIR filtering problem. Therefore, the methodology we developed for linear FIR filtering by use of the FFT applies directly. FFT algorithms. The computational problem for the DFT is to compute the sequence x of k of n complex valued numbers given another sequence of data x of n of x of k equal to summation n equal to 0 to n minus 1 x of n into wn power kr, where 0 less than or equal to k less than or equal to n minus 1, where wn equal to e power minus j 2 pi by n. In general, the data sequence x of n is also assumed to be complex valued. Similarly, the IDFT becomes x of n equal to 1 by n into summation k equal to 0 to n minus 1 x of k into wn power minus nk, 0 less than or equal to n less than or equal to n minus 1. Since the DFT and IDFT involve basically the same type of computations, the efficient computational algorithm for the DFT applies to the efficient computation of the IDFT. Direct computation of the DFT is basically inefficient primarily because it does not exploit the symmetry and periodicity properties of the phase factor Wn. In particular, these two properties are symmetry property Wn power k plus n by 2 equal to minus Wn power k is called equation number 5.5.51. Periodicity property Wn power k plus n equal to Wn power k is called equation number 5.5.2. The computationally efficient algorithms known collectively as fast Fourier transform FFT algorithm exploit these two basic properties of the phase factor. Direct computation of the DFT. For a complex valued sequence x of n points, the DFT may be expressed as xr of k equal to summation n equal to 0 to n minus 1 xr of n into cos 2 pi kn by n plus xl of n into sin 2 pi kn by n is called equation number 5.5.53. xl of k equal to minus summation n equal to 0 to n minus 1 xr of n into sin 2 pi kn by n minus x1 of n into cos 2 pi kn by n is called equation number 5.5.4. The direct computation of above requires 2n square evaluations of trigonometric functions, 4n square real multiplications, 4n into n minus 1 real additions, a number of indexing and addressing operations. These operations are typical of DFT computational algorithms. The operations in item A 2 and 3 result in the DFT values XOR of k and XL of k. The indexing and addressing operations are necessary to fetch the data x of n 0 less than or equal to n less than or equal to n minus 1 and the phase factors and to store the results. Divide and conquer approach to computation of the DFT. This approach is based on the decomposition of an n-point DFT into successively smaller DFTs. This approach leads to a family of computationally efficient algorithms known collectively as FFT algorithms. Consider the computation of an n-point DFT where n can be factored as a product of two integers, that is n equal to Lm. The assumption that n is not a prime number is not restrictive, since we can pad any sequence with zeros to ensure a factorization of the form n equal to Lm. The sequence x of n 0 less than or equal to n less than or equal to n minus 1 can be stored in either a one-dimensional array indexed by n or as a two-dimensional array indexed by L and m, where 0 less than or equal to 1 less than or equal to L minus 1 and 0 less than or equal to m less than or equal to m minus 1. L is 0 index and m is the column index. Figure two-dimensional data array for storing the sequence x of n 0 less than or equal to n less than or equal to n minus 1. A similar arrangement can be used to store the computed DFT values. In particular, the mapping is from the index k to a pair of indices p, q, where 0 less than or equal to p less than or equal to L minus 1 and 0 less than or equal to q less than or equal to m minus 1. If we select the mapping k equal to mp plus q is called equation number 5.5.5. The DFT is stored on a row-wise basis where the first row contains the first m elements of the DFT x of k, second row contains the next set of m elements and so on. On the other hand, the mapping k equal to ql plus p is called equation number 5.5.6. Results in a column-wise storage of x of k where the first L elements are stored in the first column and the second set of L elements are stored in the second column and so on. Let us adapt a column-wise mapping for x of n given by 6.1.10 and the row-wise mapping for the DFT given by 6.1.11. Then x of p, q equal to summation m equal to 0 to m minus 1 summation L equal to 0 to L minus 1 x of L, n w n power mp plus q into ml plus L is called equation number 5.5.7. But wn power mp plus q into ml plus L equal to wn power ml mp into wn power mlq into wn power mpl into wn power lq is called equation number 5.5.8. However, wn power nmp equal to 1, wn power mql equal to wn by l power mq equal to wm power mq, and wn power mpl equal to wn by m power pl equal to wl power pl. With the simplifications, 5.5.7 can be expressed as x of p, q equal to summation L equal to 0 to L minus 1 within the bracket wn power lq again within the bracket summation m equal to 0 to m minus 1 x of L, n into wm power mq outside the bracket wl power lp is called equation number 5.5.9. The expression in 5.5.9 involves the computation of DFTs of length m and length L. Computation is divided into 3 steps. Number 1. First we compute the m-point DFTs f of L, q equal to summation m equal to 0 to m minus 1 x of L, n into wm power mq where 0 less than or equal to q less than or equal to m minus 1 is called equation number 5.5.10. For each of the rows L equal to 0, 1, etc. L minus 1. This step involves the computation of L DFTs, each of m points. Hence, this step requires Lm square complex multiplications and Lm of m minus 1 complex additions. Number 2. Second, we compute a new rectangular array G of L comma Q defined as G of L comma Q equal to Wn power Lq f of L comma Q, where 0 less than or equal to L less than or equal to L minus 1, 0 less than or equal to Q less than or equal to M minus 1 is called equation number 5.5.11. This step requires the Lm complex multiplications. Number 3. Finally, we compute the L point DFTs x of P comma Q equal to summation L equal to 0 to L minus 1 G of L comma Q into WL power LQ is called equation number 5.5.12. For each column Q equal to 0, 1, etc. up to M minus 1 of the array G of L comma Q. This step requires ML square complex multiplications and ML of L minus 1 complex additions. Therefore, the computational complexity is complex multiplications n of m plus L plus 1, complex additions n of m plus L minus 2, where n equal to ml. Algorithm 1. Step 1. Store the signal column wise. Number 2. Compute the m point DFT each row. Number 3. Multiply the resulting array by the phase factors Wn power Lq. Number 4. Compute the L point DFT of each column. Number 5. Read the resulting array row wise. Algorithm 2. Number 1. Store the signal row wise. Number 2. Compute the L point DFT at each column. Number 3. Multiply the resulting array by the factors Wn power Pm. Number 4. Compute the m point DFT of each row. Number 5. Read the resulting array column wise. Radix 2 FFT algorithms. Radix 2 algorithms are the most widely used FFT algorithm. Let us consider the computation of n equal to 2 power v point DFT by the divide and conquer approach. We select m equal to n by 2 and L equal to 2. This results in a split of the n point data sequence into two n by 2 point data sequences f1 of n and f2 of n, corresponding to the even numbered and odd numbered samples of x of n respectively, that is f1 of n equal to x of 2n. f2 of n equal to x of 2n plus 1, where n equal to 0, 1, etc. n by 2 minus 1 is called equation number 5.5.13. Thus f1 of n and f2 of n are obtained by decimating x of n by a factor of 2, and hence the resulting FFT algorithm is called a decimation in time algorithm. Now, the endpoint DFT can be expressed in terms of the DFTs of the decimated sequences as follows. X of k equal to summation n equal to 0 to n minus 1, x of n into w n power kn, where k equal to 0, 1, etc. up to n minus 1, equal to summation n even x of n into w n power kn plus summation n naught x of n into w n power an, equal to summation m equal to 0 to n by 2 minus 1 x of 2m into w n power 2mk plus summation m equal to 0 to n by 2 minus 1 x of 2m plus 1 into w n power k of 2m plus 1. But wn square equal to wn by 2, with the substitution 5.5.14 can be expressed as x of k equal to summation m equal to 0 to n by 2 minus 1 f1 of m into w n by 2 power km plus w n power k summation m equal to 0 to n by 2 minus 1 f2 of m into w n by 2 power km equal to f1 of k plus w n power k into f2 of k, where k equal to 0, 1, etc. up to n minus 1 is called equation number 5.5.15, where f1 of k and f2 of k are the n by 2 point DFTs of the sequences f1 of m and f2 of m respectively. Since f1 of k and f2 of k are periodic with period n by 2, we have f1 of k plus n by 2 equal to f1 of k and f2 of k plus n by 2 equal to f2 of k. In addition, the factors wn power k plus n by 2 equal to minus wn power k. Hence, 5.5.25 can be expressed as x of k equal to f1 of k plus Wn power k into f2 of k where k equal to 0, 1, etc. n by 2 minus L is called equation number 5.5.16. X of k plus n by 2 equal to f1 of k minus Wn power k into f2 of k where k equal to 0, 1, etc. n by 2 minus 1 is called equation number 5.5.17. We observe that the direct computation of f1 of k requires n by 2 the whole square complex multiplications. The same applies to the computation of f2 of k. Furthermore, there are n by 2 additional complex multiplications required to compute Wn power k f2 of k. Hence, the computation of x of k requires 2 of n by 2 the whole square plus n by 2 equal to n square by 2 plus n by 2 complex multiplications. The first step results in a reduction of the number of multiplications from n square to n square by 2 plus n by 2, which is about a factor of 2 for n large. To be consistent with our previous notation, we may define g1 of k equal to f1 of k where k equal to 0, 1, etc. up to n by 2 minus 1, g2 of k equal to wn power k into f2 of k where k equal to 0, 1, etc. n by 2 minus 1. Then the DFT x of k may be expressed as x of k equal to g1 of k plus g2 of k where k equal to 0, 1, etc. up to n by 2 minus 1. X of k plus n by 2 equal to g1 of k minus g2k where k equal to 0, 1, etc. n by 2 minus 1 is called equation number 5.5.18. First steps in the decimation in time algorithm. Having performed the decimation in time once, we can repeat the process for each of the sequences f1 of n and f2 of n. Thus, f1 of n would result in the 2n by 4 point sequences. v11 of n equal to f1 of 2n where n equal to 0, 1, etc. n by 4 minus 1. v12 of n equal to f1 of 2n plus 1 where n equal to 0, 1, etc. n by 4 minus 1 is called equation number 5.5.19. And f2 of n would yield v21 of n equal to f2 of 2n where n equal to 0, 1, etc. n by 4 minus 1. v22 of n equal to f2 of 2n plus 1 where n equal to 0, 1, etc. n by 4 minus 1 is called equation number 5.5.20. By computing n by 4 point DFTs, we would obtain the n by 2 point DFTs f1 of k and f2 of k from the relations f1 of k equal to v11 of k and w n by 2 power k v12 of k where k equal to 0, 1, etc. n by 4 minus 1. f1 of k plus n by 4 equal to v11 of k minus w n by 2 power k into v12 of k where k equal to 0, 1, etc. n by 4 minus 1. f2 of k equal to v21 of k plus w n by 2 power k v22 of k where k equal to 0, 1, etc. n by 4 minus 1. f2 of k plus n by 4 equal to v21 of k minus w n by 2 power k into v22 of k where k equal to 0, etc. n by 4 minus 1. Where the vi, j, k are the n by 4 point DFTs of the sequences vi, j, n. We observe that the computation of vi, j, k requires 4 of n by 4 whole square multiplications, and hence the computation of f1 of k and f2 of k can be accomplished with n square by 4 plus n by 2 complex multiplications. An additional n by 2 complex multiplications are required to x of k from f1 of k and f2 of k. Consequently, the total number of multiplications is reduced approximately by a factor of 2 again to n square by 4 plus n. The decimation of the data sequence can be repeated again and again until the resulting sequences are reduced to 1 point sequences for n equal to 2 power v. This decimation can be performed v equal to log 2n times. Thus, the total number of complex multiplications is reduced to n by 2 log 2n. The number of complex additions is n into log 2n. Table: comparison of computational complexity for the direct computation of the DFT versus the FFT algorithm. 3 stages in the computation of an n equal to 8 point DFT. 8-point decimation in time FFT algorithm. The basic computation performed at every stage is to take two complex numbers, say the pair a, b, multiply b by wn power r, and then add and subtract the product from a to form two new complex numbers a, b. This basic computation is called a butterfly. In general, each butterfly involves one complex multiplication and two complex additions. For n equal to 2 power b, there are n by 2 butterflies per stage of the computation process and log 2n stages. Therefore, the total number of complex multiplications is n by 2 log 2n and complex additions is n log 2n. Once a butterfly operation is performed on a pair of complex numbers a, b to produce a, b, there is no need to say the input pair a, b. Hence, we can store the result a, b in the same locations as a, b. We require a fixed amount of storage in order to store the results. Since the same 2n storage locations are used throughout the computation of the endpoint DFT, we say the computations are done in place. Another important radix 2 FFT algorithm called the decimation frequency algorithm is obtained by using the divide and conquer approach with the choice m equal to 2 and l equal to n by 2. To derive the algorithm, we begin by splitting the DFT formula into two summations, one of which involves the sum over the first n by 2 data points and the second sum involves the last n by 2 data points. Thus, we obtain x of k equal to summation n equal to 0 to n by 2 minus 1 x of n into wn power kn plus summation n equal to n by 2 to n minus 1 x of n into wn power kn equal to summation n equal to 0 to n by 2 minus 1 x of n into wn power kn plus wn power nk by 2 into summation n equal to 0 to n by 2 minus 1 x of n plus n by 2 into wn power kn. Since wn power kn by 2 equal to minus 1 whole power k, the above expression can be written as x of k equal to summation n equal to 0 to n by 2 minus 1 x of n plus minus 1 whole power k into x of n plus n by 2 into wn power kn. Let us split decimate x of k into the even and odd numbered samples. Thus, we obtain x of 2k equal to summation n equal to 0 to n by 2 minus 1 x of n plus x of n plus n by 2 into wn by 2 power kn, where k equal to 0, 1, etc. n by 2 minus 1, and x of 2k plus 1 equal to summation n equal to 0 to n by 2 minus 1 x of n minus x of n plus n by 2 into wn power n outside the bracket wn by 2 power kn, where k equal to 0, 1, etc. n by 2 minus 1, where we have used the fact wn square equal to wn by 2. If we define the n by 2 point sequences g1 of n and g2 of n as g1 of n equal to x of n plus n by 2, g2 of n equal to x of n minus x of n plus n by 2 into wn power n, where n equal to 0, 1, 2, etc. n by 2 minus 1. Then x of 2k equal to summation n equal to 0 to n by 2 minus 1 g1 of n into wn by 2 power kn. X of 2k plus 1 equal to summation n equal to 0 to n by 2 minus 1 g2 of n into wn by 2 power kn. First stage of the decimation in frequency FFT algorithm. Basic butterfly computation in the decimation in frequency FFT algorithm. N equal to 8-point decimation in frequency FFT algorithm. Radix 4 FFT algorithms. Radix 4 decimation in time FFT algorithm is obtained by selecting L equal to 4 and M equal to n by 4 in the divide and conquer approach. For this choice of L and M, we have L, P equal to 0, 1, 2, 3, M, Q equal to 0, 1, etc. n by 4 minus 1, n equal to 4m plus 1 and k equal to n by 4 p plus q. Thus, we split or decimate the n-point input sequence into 4 subsequences x of 4n plus 1, x of 4n plus 2, x of 4n plus 3 n equal to 0, 1, etc. n by 4 minus 1. By applying x of p comma q equal to summation L equal to 0 to L minus 1 within the bracket W n power LQ summation m equal to 0 to m minus 1 x of L comma m W m power mq outside the bracket W L power LP. We obtain x of p comma q equal to summation L equal to 0 to 3 W n power LQ f of L comma q W4 power LP where p equal to 0, 1, 2, 3. Where f of L comma q is given by f of L comma q equal to summation m equal to 0 to n by 4 minus 1 x of L comma m into W n by 4 power mq where L equal to 0, 1, 2, 3, q equal to 0, 1, 2, etc. n by 4 minus L and x of L comma m equal to x of 4m plus L x of p comma q equal to x of n by 4 into p plus q. The n by 4 point DFT is defined as radix 4 decimation in time butterfly which can be expressed in matrix form as basic butterfly computation in a radix 4 FFT algorithm. By performing the additions in 2 steps, it is possible to reduce the number of additions per butterfly from 12 to 8. The matrix of the linear transformation as a product of 2 matrices. A radix 4 decimation in frequency FFT algorithm can be obtained by selecting L equal to n by 4, m equal to 4, L comma p equal to 0, 1, etc. n by 4 minus 1, m comma q equal to 0, 1, 2, 3, n equal to n by 4 of m plus 1 and k equal to 4p plus q. With the choice of parameters x of p comma q equal to summation L equal to 0 to L minus 1 W n power LQ of summation m equal to 0 to m minus 1 x of L comma m into W m power m outside the bracket W L power LP can be expressed as x of p comma q equal to summation L equal to 0 to n by 4 minus 1 g of L comma q into W n by 4 power LP, where g of L comma q equal to W n power LQ f of L comma q equal to 0, 1, 2, 3, L equal to 0, 1, etc. n by 4 minus 1 and f of L comma q equal to summation m equal to 0 to 3 x of L comma m into W4 power mq where L equal to 0, 1, 2, 3, etc. n by 4 minus 1. The radix 4 decimation in frequency algorithm is derived by breaking the n-point DFT formula into 4 smaller DFTs. X of k equal to summation n equal to 0 to n minus 1 x of n into W n power kn equal to summation n equal to 0 to n by 4 minus 1 x of n into W n power kn plus summation n equal to n by 4 to n by 2 minus 1 x of n into W n power kn plus summation n equal to n by 2 3n by 4 minus 1 x of n into W n power kn plus summation n equal to 3n by 4 to n minus 1 x of n into W n power kn equal to summation n equal to 0 to n by 4 minus 1 x of n into W n power kn plus W n power n L by 4 into summation n equal to 0 to n by 4 minus 1 x of n plus n by 4 into W n power kn plus W n power kn by 2 into summation n equal to 0 to n by 4 minus 1 x of n plus n by 2 into W n power nk plus W n power 3 kn by 4 into summation n equal to 0 to n by 4 minus 1 x of n plus 3n by 4 into W n power kn is called equation number 5.5.20. From the definition of twiddle factor, we have W n power kn by 4 equal to minus j whole power k, W n power nk by 2 equal to minus 1 whole power k, W n power 3nk by 4 equal to j power k is called equation number 5.5.21. After substituting 5.5.21 into 5.5.20, we obtain x of k equal to summation n equal to 0 to n by 4 minus 1 x of n plus minus j whole power k, x of n plus n by 4 plus minus 1 whole power k into x of n plus n by 4 plus j power k into x of n plus 3n by 4 outside the bracket wn power nk is called equation number 5.5.22. The relation in 5.5.22 is not an n by 4 point DFT because the twiddle factor depends on n and not on n by 4. To convert it into an n by 4 point DFT, we subdivide the DFT sequence into 4 n by 4 point subsequences x of 4k, x of 4k plus 1, x of 4k plus 2 and x of 4k plus 3, where k equal to 0, 1 etc. n by 4 minus 1. The radix for decimation in frequency DFT as x of 4k equal to summation n equal to 0 to n by 4 minus 1, x of n plus x of n plus n by 4 plus x of n plus n by 2 plus x of n plus 3n by 4 outside the bracket w n power 0 into w n by 4 power kn. X of 4k plus 1 equal to summation n equal to 0 to n by 4 minus 1, x of n minus jx of n plus n by 4 minus x of n plus n by 2 plus jx of n plus 3n by 4 outside the bracket wn power n into w n by 4 power kn. X of 4k plus 2 equal to summation n equal to 0 to n by 4 minus 1, x of n minus x of n plus n by 4 plus x of n plus n by 2 minus x of n plus 3n by 4 outside the bracket wn power 2n into wn by 4 power kn. X of 4k plus 3 equal to summation n equal to 0 to n by 4 minus 1, x of n plus jx of n plus n by 4 minus x of n plus n by 2 minus jx of n plus 3n by 4 outside the bracket wn power 3n into wn by 4 power kn, where we have used the property wn power 4 kn equal to wn by 4 power kn. Split radix FFT algorithms. Split radix FFT SR FFT algorithms uses both the radix 2 and a radix 4 decomposition in the same FFT algorithm. A radix 4 decimation in frequency FFT algorithm for the odd numbered samples of the n point DFT, x of 4k plus 1 equal to summation n equal to 0 to n by 4 minus 1, x of n minus x of n plus n by 2 minus j times of x of n plus n by 4 minus x of n plus 3n by 4 outside the bracket wn power n into wn by 4 power kn. X of 4k plus 3 equal to summation n equal to 0 to n by 4 minus 1, x of n minus x of n plus n by 2 plus j times of x of n plus n by 4 minus x of n plus 3n by 4 outside the bracket wn power 3n into wn by 4 power kn. The n point DFT is decomposed into 1 n by 2 point DFT without additional twiddle factors and 2 n by 4 point DFTs with twiddle factors. The computation for n equal to 32. The top 16 points constitute the sequence g0 of n equal to x of n plus x of n plus n by 2, 0 less than or equal to n less than or equal to 15. The next 8 points constitute the sequence g1 of n equal to x of n minus x of n plus n by 2, 0 less than or equal to n less than or equal to 7. The bottom 8 points constitute the sequence g2 of n, where g2 of n equal to x of n plus n by 4 minus x of n plus 3n by 4, 0 less than or equal to n less than or equal to 7. The computation of 16-point DFT is done by decomposing the computation into an 8-point radix 2 DFT and 2 4-point radix 4 DFTs. The top 8 points constitute the sequence with n equal to 16. g0 dash of n equal to g0 of n plus g0 of n plus n by 2, 0 less than or equal to n less than or equal to 7. And the next 8 points constitute the two 4-point sequences. G1 dash of n equal to G0 of n minus G0 of n plus n by 2, 0 less than or equal to n less than or equal to 3. G2 dash of n equal to G0 of n plus n by 4 minus G0 of n plus 3n by 4, 0 less than or equal to n less than or equal to 3. The number of total factors that must be computed and stored in reduced by a factor of 2 in comparison to DUML algorithm. The resulting algorithm is called the mirror FFT, MFFT. An additional factor of 2 savings in storage of total factors can be obtained by introducing a 90-degree phase offset at the midpoint of each twiddle array, which can be removed if necessary at the output of the SRFFT computation. The incorporation of this improvement into the SRFFT or MFFT results in another algorithm also due to Price 1990 called the phase FFT PFFT algorithm. Frequency analysis of signal using the DFT. In this section, we examine the implications of a finite data record in frequency analysis using the DFT. If the signal to be analyzed is an analog signal, we would first pass it through an anti-aliasing filter and then sample it at a rate fs greater than or equal to 2b, where b is the bandwidth of the filtered signal. Thus, the highest frequency that is contained in the sampled signal is fs by 2. Finally, for practical purposes, we limit the duration of the signal to the time reversal t0 equal to lt, where L is the number of samples and T is the sample interval. Let x of n denote the sequence to be analyzed, limiting the duration of the sequence to L samples in the interval 0 less than or equal to n less than or equal to L minus 1 is equivalent to multiplying x of n by a rectangular window omega of n of length L, that is x cap of n equal to x of n into omega of n, where omega of n equal to 1 for 0 less than or equal to n less than or equal to L minus 1 and 0 otherwise. Now suppose that the sequence x of n consists of a single sinusoid, that is x of n equal to cos omega naught of n. Then the Fourier transform of the finite duration sequence x of n can be expressed as x cap of omega equal to 1 by 2 times of w of omega minus omega naught plus w of omega plus omega naught, where w of omega is the Fourier transform of the window sequence, which is for the rectangular window. W of omega equal to sin omega L by 2 divided by sin omega by 2 into e power minus j omega of L minus 1 by 2. To compute x of omega, we use the DFT. By padding the sequence x cap of n with n minus L zeros, we can compute the n point DFT of the truncated L point sequence x cap of n. The power of the original signal sequence x of n that was concentrated at a single frequency has been spread by the window into the entire frequency range. We say that the power has leaked out into the entire frequency range. Consequently, this phenomenon, which is a characteristic of windowing the signal, is called leakage. Magnitude spectrum for L equal to 25 and n equal to 208 illustrating the occurrence of leakage. Windowing not only distorts the spectral estimate due to the leakage effects, it also reduces spectral resolution. To illustrate this problem, let us consider a signal sequence consisting of two frequency components x of n equal to cos omega 1n plus cos omega 2n. When the sequence is truncated to L samples in the range 0 to L minus 1, the windowed spectrum is x cap of omega equal to 1 by 2 times of w of omega minus 1 plus w of omega minus 2 plus w of omega plus omega 1 plus w of omega plus omega 2. The spectrum w of omega of the rectangular window sequence has its first zero crossing at omega equal to 2 pi by L. Now if modulus of omega 1 minus omega 2 less than 2 pi by L, the two window functions w of omega minus omega 1 and w of omega minus omega 2 overlap, and as a consequence the two spectral lines in x of n are not distinguishable. Only if omega 1 minus omega 2 greater than or equal to 2 pi by L will we see two separate lobes in the spectrum x cap of omega. Thus our ability to resolve spectral lines of different frequencies is limited by the window main lobe width. The magnitude spectrum modulus of x of omega computed via the DFT for the sequence x of n equal to cos omega naught of n plus cos omega 1 of n plus cos omega 2 of n, where omega naught equal to 0.2 pi, omega 1 equal to 0.22 pi and omega 2 equal to 0.6 pi. The window lengths selected are L equal to 25, 50 and 100. Note that omega naught and omega 1 are not resolvable for L equal to 25 and 50, but they are resolved for L equal to 100. To reduce leakage, we can select data window omega of n that has lower side lobes in the frequency domain compared with the rectangular window. A reduction of the side lobes in a window W of omega is obtained at the expense of an increase in the width of main lobe of W of omega and hence loss in resolution. Let us consider the Hanning window, which is specified as omega of n equal to 1 by 2 of 1 minus cos 2 pi by L minus 1 into n, where 0 less than or equal to n less than or equal to L minus 1 and 0 otherwise. Magnitude spectrum of the Hanning window. Its side lobes are significantly smaller than those of rectangular window, but its main lobe is approximately twice as wide. The reduction of the side lobes and the decrease in the resolution compared with the rectangular window is now clearly evident. For a general signal sequence x of n, the frequency domain relationship between the windowed sequence x of n and the original sequence x of n is given by the convolution formula. X cap of omega equal to 1 by 2 pi integral minus pi to pi x of theta into w of omega minus theta into d theta. The DFT of the windowed sequence x of n is a sampled version of the spectrum x of omega. Thus we have x cap of k equivalent to x cap of omega equal to 2 pi k by n equal to 1 by 2 pi integral minus pi to pi x of theta into w of 2 pi k by n minus theta into d theta, where k equal to 0 and etc. n minus 1. Magnitude spectrum of the signal in x of n equal to cos omega naught n plus cos omega n plus cos omega 2n as observed through a Hanning window. Frequency domain sampling, the discrete Fourier transform. Before we introduce DFT, we consider the sampling of the Fourier transform of an periodic discrete time sequence. Thus we establish the relationship between the sampled Fourier transform and the DFT. Frequency domain sampling and reconstruction of discrete time signals. The periodic finite energy signals have continuous spectra. Let us consider such an aperiodic discrete time signal x of n with Fourier transform. X of omega equal to summation n equal to minus infinity to plus infinity x of n into e power minus j omega n. If we evaluate above equation at omega equal to 2 pi k by n, we obtain x of 2 pi by n into k equal to summation n equal to minus infinity to plus infinity x of n into e power minus j 2 pi k n by n, where k equal to 0, 1 etc. up to n minus 1. The summation in above equation can be subdivided into an infinite number of summations where each sum contains n terms. Thus x of 2 pi by n into k equal to etc. plus summation n equal to minus n to minus 1 x of n into e power minus j 2 pi k n by n plus summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n plus summation n equal to n to 2n minus 1 x of n into e power minus j 2 pi k n by n plus etc. equal to summation L equal to minus infinity to plus infinity into summation nl to ln plus n minus l x of n into e power minus j 2 pi k n by n. If we change the index in the inner summation from n to n minus 1 n and interchange the order of the summation, we obtain the result x of 2 pi by n into k equal to summation n equal to 0 to n minus 1 into within the bracket summation L equal to minus infinity to plus infinity x of n minus ln outside the bracket e power minus j 2 pi k n by n, where k equal to 0, 1, etc. up to n minus 1. The signal xp of n equal to summation L equal to minus infinity to plus infinity x of n minus ln, obtained by the periodic repetition of x of n. Every n samples is clearly periodic with fundamental period n. Consequently, it can be expanded in a Fourier series as xp of n equal to summation k equal to 0 to n minus 1 ck into e power j 2 pi k n by n, where n equal to 0, 1, etc. up to n minus 1, with Fourier coefficient ck equal to 1 by n summation n equal to 0 to n minus 1 xp of n into e power minus j 2 pi k n by n, where k equal to 0, 1, etc. up to n minus 1. Upon comparing above equations, we conclude that ck equal to 1 by n into x of 2 pi by n into k, where k equal to 0, 1, etc. up to n minus 1. Therefore, xp of n equal to 1 by n summation k equal to 0 to n minus 1 x of 2 pi by n into k e power j 2 pi k n by n, where n equal to 0, 1, etc. up to n minus 1. The relationship provides the reconstruction of the periodic signal xp of n from the samples of the spectrum x of omega. However, it does not imply that we can recover x of omega or x of n from the samples. To accomplish this, we need to consider the relationship between xp of n and x of n. Since xp of n is the aperiodic extension of x of n, it is clear that x of n can be recovered from xp of n if there is no aliasing in the time domain, that is, if x of n is time limited to less than the period n of xp of n. Consider a finite duration sequence x of n which is non-zero in the interval 0 less than or equal to n less than or equal to l minus 1. We observe that when n greater than or equal to l, x of n equal to xp of n, where 0 less than or equal to n less than or equal to n minus 1, so that x of n can be recovered from xp of n without ambiguity. On the other hand, if n less than l, it is not possible to recover x of n from its periodic extension due to time domain aliasing. Thus, we conclude that the spectrum of an aperiodic discrete time signal with a finite duration L can be exactly recovered from its samples at frequencies omega k equal to 2 pi k by n if n greater than or equal to L. The procedure is to compute xp of n, where n equal to 0, 1, etc. up to n minus 1, then x of n equal to xp of n for 0 less than or equal to n less than or equal to n minus 1 and 0 elsewhere. And finally, x of omega can be computed. As in the case of continuous time signals, it is possible to express the spectrum x of omega directly in terms of its samples x of 2 pi k by n, where k equal to 0, 1, etc. up to n minus 1. To derive such an interpolation formula for x of omega, we assume that n greater than or equal to L, since x of n equal to xp of n for 0 less than or equal to n less than or equal to n minus 1. X of n equal to 1 by n into summation k equal to 0 to n minus 1 x of 2 pi by n into k into e power j 2 pi k n by n 0 less than or equal to n less than or equal to n minus 1. X of omega equal to summation n equal to 0 to n minus 1 into within the bracket 1 by n into summation k equal to 0 to n minus 1 x of 2 pi by n into k e power j 2 pi k n by n into, that means outside the bracket, e power minus j omega n equal to summation k equal to 0 to n minus 1 x of 2 pi by n into k into within the bracket 1 by n into summation n equal to 0 to n minus 1 e power minus j omega minus 2 pi k by n. The inner summation term in the brackets represents the basic interpolation function shifted by 2 pi k by n in frequency. Indeed, if we define p of omega equal to 1 by n into summation n equal to 0 to n minus 1, e power minus j omega n equal to 1 by n into 1 minus e power minus j omega n by e power minus j omega equal to sin of omega n by 2 divided by n into sin of omega by 2 into e power minus j omega of n minus 1 by 2. The x of omega can be expressed as x of omega equal to summation k equal to 0 to n minus 1 x of 2 pi by n into k into p of omega minus 2 pi by n into k, where n greater than or equal to L. The interpolation function p of omega is not the familiar sin theta by theta, but instead it is a periodic counterpart of it, and it is due to the periodic nature of x of omega. The phase shift reflects the fact that the signal x of n is a causal finite duration sequence of length n. We observe that the function p of omega has the property p of 2 pi by n into k equal to 1 for k equal to 0, 0 for k equal to 1 to etc. n minus 1. Example: consider the signal s of n equal to a power n into u of n, where 0 less than a less than 1. The spectrum of the signal is sampled at frequencies omega k equal to 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. Determine the reconstructed spectra for a equal to 0.8 when n equal to 5 and n equal to 50. Solution: the Fourier transform of the sequence x of n is x of omega equal to summation n equal to 0 to infinity a power n into e power minus j omega n equal to 1 divided by 1 minus a into e power minus j omega. Suppose that we sample x of omega at n equidistant frequencies omega k equal to 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. Thus we obtain the spectral samples x of omega k equal to x of 2 pi k divided by n equal to 1 divided by 1 minus a into e power minus j 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. The periodic sequence xp of n corresponding to the frequency samples x of 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. Xp of n equal to summation I equal to minus infinity to plus infinity x of n minus ln equal to summation L equal to minus infinity to 0 a power n minus ln equal to a power n into summation L equal to 0 to infinity a power ln equal to a power n divided by 1 minus a power n, where 0 less than or equal to n less than or equal to n minus 1, where the factor 1 divided by 1 minus a power n represents the effect of aliasing, since 0 less than a less than 1. The aliasing error tends towards 0 as n tends to infinity. If we define the aliased finite duration sequence x of n as x cap of n equal to xp of n, where 0 less than or equal to n less than or equal to n minus 1 and 0 otherwise, then its Fourier transform is x cap of omega equal to summation n equal to 0 to n minus 1 x cap of n into e power minus j omega n equal to summation n equal to 0 to n minus 1 xp of n into e power minus j omega n equal to 1 divided by 1 minus a power n into 1 minus a power n into e power minus j omega n divided by 1 minus a into e power minus j omega. Note that although x cap of omega not equal to x of omega, the sample values at omega k equal to 2 pi k divided by n are identical, then it's x cap of 2 pi by n into k equal to 1 divided by 1 minus a power n into 1 minus a power n divided by 1 minus a into e power minus j 2 pi k n equal to x of 2 pi by n into k. The discrete Fourier transform DFT. The equally spaced frequency samples x of 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1 do not uniquely represent the original sequence x of n when x of n has infinite duration. Instead, the frequency samples x of 2 pi k divided by n, where k equal to 0, 1, etc. n minus 1, corresponding to a periodic sequence xp of n of period n, where xp of n is an aliased version of x of n, that is, xp of n equal to summation L equal to minus infinity to plus infinity x of n minus Ln. When the sequence is x of n has a finite duration of length L less than or equal to n, then xp of n is simply a periodic repetition of x of n, where xp of n over a single period is given as xp of n equal to x of n, where 0 less than or equal to n less than or equal to L minus 1, and 0 for L less than or equal to n less than or equal to n minus 1. Consequently, the frequency samples x of 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1, uniquely represent the finite duration sequence x of n. Since x of n equivalent to xp of n over a single period padded by n minus L zeros, the original finite duration sequence x of n can be obtained from the frequency samples x of 2 pi k divided by n. It is important to note that zero padding does not provide any additional information about the spectrum x of omega of the sequence x of n. The L equidistant samples of x of n are sufficient to reconstruct x of omega using the reconstruction formula. However, padding the sequence x of n with n minus L zeros and computing an n-point DFT results in a better display of the Fourier transform x of omega. In summary, a finite duration sequence x of n of length L, that is, x of n equal to 0 for n less than 0 and n greater than or equal to L, as a Fourier transform x of omega equal to summation n equal to 0 to L minus 1 x of n into e power minus j omega n, where 0 less than or equal to omega less than or equal to 2 pi. When we sample x of omega at equally spaced frequencies omega k equal to 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1, where n greater than or equal to L, the resultant samples are x of k equivalent to x of 2 pi k divided by n equal to summation n equal to 0 to L minus 1 x of n into e power minus j 2 pi k n by n. X of k equal to summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where k equal to 0, 1, 2, etc. up to n minus 1. Where for convenience, the upper index in the sum has been increased from L minus 1 to n minus 1, since x of n equal to 0 for n greater than or equal to L. The frequency samples obtained by evaluating the Fourier transform x of omega at a set of n equally spaced discrete frequencies, the relation is called the discrete Fourier transform DFT of x of n. The relation which allows us to recover the sequence x of n from the frequency samples is called the inverse DFT, IDFT. The formulas for the DFT and IDFT are DFT x of k equal to summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where k equal to 0, 1, 2, etc. up to n minus 1. IDFT x of n equal to 1 by n summation k equal to 0 to n minus 1 x of k into e power j 2 pi k n by n, where n equal to 0, 1, 2, etc. up to n minus 1. Example: a finite duration sequence of length L is given as x of n equal to 1 for 0 less than or equal to n less than or equal to L minus 1 and 0 otherwise. Determine the n-point DFT of the sequence for n greater than or equal to L. Solution: the Fourier transform of the sequences x of omega equal to summation n equal to 0 to L minus 1 x of n into e power minus j omega n equal to summation n equal to 0 to L minus 1 e power minus j omega n equal to 1 minus e power minus j omega L divided by 1 minus e power minus j omega equal to sin of omega L by 2 divided by sin of omega by 2 into e power minus j omega of L minus 1 by 2. The endpoint DFT of x of n is simply x of omega evaluated at the set of n equally spaced frequencies omega k equal to 2 pi k divided by n, where k equal to 0, 1 etc. up to n minus 1. Hence x of k equal to 1 minus e power minus j 2 pi k L by n divided by 1 minus e power minus j 2 pi k L by n, where k equal to 0, 1 etc. up to n minus 1 equal to sin of pi k L by n divided by sin of pi k by n into e power minus j pi k of L minus 1 by n. If n is selected such that n equal to L, then the DFT becomes x of k equal to L for k equal to 0, 0 for k equal to 1, 2 etc. up to L minus 1. Thus there is only one non-zero value in the DFT. The L point DFT is sufficient to uniquely represent the sequence x of n in the frequency domain. It is apparent that it does not provide sufficient detail to yield a good picture of the spectral characteristics of x of n. The DFT as a linear transform. The formulas for the DFT and IDFT may be expressed as x of k equal to summation n equal to 0 to n minus 1 x of n into w n k n, x of n equal to 1 by n into summation k equal to 0 to n minus 1 x of k into w n minus k n, where n equal to 0, 1 etc. up to n minus 1, where by definition w n equal to e power minus j 2 pi by n, which is an nth root of unity. We note that the computation of each point of the DFT can be accomplished by n complex multiplications and n minus 1 complex additions. Hence, the n point DFT values can be computed in a total of n square complex multiplications n into n minus 1 complex additions. Let us define an n point vector xn of the signal sequence x of n, where n equal to 0, 1 etc. up to n minus 1, an n point vector xn of frequency samples and an n cross n matrix wn as shown in the matrix. With these definitions, the n point DFT may be expressed in matrix form as xn equal to wn into xn, where wn is the matrix of the linear transformation. We observe that wn is a symmetric matrix. If we assume that the inverse of wn exists, then above equation can be inverted by pre-multiplying both sides by wn power minus 1. Thus we obtain xn equal to wn power minus 1 into xn. The IDFT can be expressed in matrix form as xn equal to 1 by n wn star into xn, where wn star denotes the complex conjugate of the matrix wn. Comparison of above equations leads us to conclude that wn power minus 1 equal to 1 by n into wn star, which in turn implies that wn into wn star equal to n into in, where in is an n cross n identity matrix. Therefore, the matrix wn in the transformation is an orthogonal unitary matrix. Furthermore, its inverse exists and is given as wn star by n. Example: compute the DFT of the 4-point sequence x of n equal to 0, 1, 2, 3. Solution: the first step is to determine the matrix W4 by exploiting the periodicity property of W4 and the symmetry property. Wn power k plus n by 2 equal to minus Wn power L. The matrix W4 may be expressed as W4 equal to, we can see in the matrix, then x4 equal to w4 into x4 is shown. The IDFT of x4 may be determined by conjugating the elements in w4 to obtain w4 star and then applying the formula xn equal to 1 by n into wn star into xn. Relationship of the DFT to other transforms. The DFT is an important computational tool for performing frequency analysis of signals on digital signal processes. In view of the other frequency analysis tools and transforms that we have developed, it is important to establish the relationships between the DFT to these other transforms. Relationship to the Fourier series coefficients of a periodic sequence. A periodic sequence xp of n with a fundamental period n can be represented in a Fourier series of the form xp of n equal to summation k equal to 0 to n minus 1 ck into e power j 2 pi k divided by n, where minus infinity less than n less than infinity, where the Fourier series coefficients are given by the expression ck equal to 1 by n into summation n equal to 0 to n minus 1 xp of n into e power minus j 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. If we compare above equations with x of k equal to summation n equal to 0 to n minus 1 x of n into e power minus j 2 pi k n by n, where k equal to 0, 1, 2, etc. up to n minus 1, and x of n equal to 1 by n summation k equal to 0 to n minus 1 x of k into e power j 2 pi k n by n, where n equal to 0, 1, 2, etc. up to n minus 1. We observe that the formula for the Fourier series coefficients has the form of a DFT. In fact, if we define a sequence x of n equal to xp of n, where 0 less than or equal to n less than or equal to n minus 1, the DFT of the sequence is simply x of k equal to n into ck. Furthermore, xp of n has the form of an IDFT, thus the endpoint DFT provides the exact line spectrum of a periodic sequence with fundamental period n. Relationship to the Fourier transform of an aperiodic sequence. If x of n is an aperiodic finite energy sequence with Fourier transform x of omega, which is sampled at n equally spaced frequencies of omega, k equal to 2 pi k by n, where k equal to 0, 1, etc. up to n minus 1. The spectral components. X of k equal to x of omega, where omega equal to 2 pi k by n equal to summation n equal to minus infinity to plus infinity x of n equal to e power minus j 2 pi n k by n, where k equal to 0, 1, etc. up to n minus 1, are the DFT coefficients of the periodic sequence of period n, given by xp of n equal to summation L equal to minus infinity to plus infinity x of n minus Ln. Thus xp of n is determined by aliasing x of n over the interval 0 less than or equal to n less than or equal to n minus 1. The finite duration sequence x cap of n equal to xp of n for 0 less than or equal to n less than or equal to n minus 1 and 0 otherwise bears no resemblance to the original sequence x of n unless x of n is of finite duration and length L less than or equal to n, in which case x of n equal to x cap of n, where 0 less than or equal to n less than or equal to n minus 1. Only in this case will the IDFT of x of k yield the original sequence x of n. Relationship to the Z transform. Let us consider the sequence x of n having the Z transform x of z equal to summation n equal to minus infinity to plus infinity x of n into z power minus n with a ROC that includes the unit circle. If x of z is sampled at the n equally spaced points on the unit circle zk equal to e power j 2 pi k divided by n 0, 1, 2 etc. up to n minus 1, we obtain x of k equivalents to x of z at z equal to e power j 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1 equal to summation n equal to minus infinity to plus infinity x of n into e power minus j 2 pi nk by n. The above expression is identical to the Fourier transform x of omega evaluated at the n equally spaced frequencies omega k equal to 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. If the sequence x of n has a finite duration of length n or less, the sequence can be recovered from its endpoint DFT. Hence, its Z transform is uniquely determined by its endpoint DFT. Consequently, x of z can be expressed as function of the DFT x of k as follows. X of z equal to summation n equal to 0 to n minus 1 x of n into z power minus n. X of z equal to summation n equal to 0 to n minus 1 into within the bracket 1 by n into summation k equal to 0 to n minus 1 x of k into e power j 2 pi k n by n into, that means outside the bracket, z power minus n. Then x of z equal to 1 by n into summation k equal to 0 to n minus 1 x of k into summation n equal to 0 to n minus 1 e power j 2 pi k by n into z power minus n whole power n. X of z equal to 1 minus z power minus n divided by n into summation k equal to 0 to n minus 1 x of k divided by 1 minus e power j 2 pi k divided by n into z power minus 1. When evaluated on the unit circle, the Fourier transform of the finite duration sequence in terms of its DFT in the form x of omega equal to 1 minus e power minus j omega n divided by n into summation k equal to 0 to n minus 1 x of k divided by 1 minus e power minus j into omega minus 2 pi k divided by n. This expression for the Fourier transform is a polynomial Lagrange interpolation formula for x of omega, expressed in terms for the values x of k of the polynomial at a set of equally spaced discrete frequencies omega k equal to 2 pi k divided by n, where k equal to 0, 1, etc. up to n minus 1. Relationship to the Fourier series coefficients of a continuous time signal. Suppose that xa of f is a continuous time periodic signal with the fundamental period Tp equal to 1 divided by f0. The signal can be expressed in a Fourier series. Xa of t equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f0, where ck are the Fourier coefficients if we sample xa of t at a uniform rate fs equal to n divided by tp equal to 1 divided by t. We obtain the discrete time sequence x of n equivalents to xa of nt equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi k f0 nt equal to summation k equal to minus infinity to plus infinity ck into e power j 2 pi k n by n equal to summation k equal to 0 to n minus 1 into summation l equal to minus infinity to plus infinity ck minus ln into e power j 2 pi k n by n. It is clear that above equation is in the form of an IDFT formula, where x of k equal to n into summation l equal to minus infinity to plus infinity ck minus l n equivalents to n ck cap, and ck cap equal to summation l equal to minus infinity to plus infinity ck minus ln. Thus, the ck sequence is an aliased version of the sequence ck. Introduction. Discrete Fourier transform. Frequency analysis of discrete time signals is usually and most conveniently performed on a digital signal processor which may be a general purpose digital computer or a specially designed digital hardware. To perform frequency analysis on a discrete time signal x of n, we convert the time domain sequence to an equivalent frequency domain representation. Such a representation is given by Fourier transform x of omega of the sequence. However, x of omega is a continuous function of frequency and therefore it is not a computationally convenient representation of the sequence x of n. In this chapter, we consider the representation of a sequence x of n by samples of its spectrum x of omega. Such a frequency domain representation leads to the discrete Fourier transform DFT, which is a powerful computational tool for performing frequency analysis of discrete time signals. Linear filtering method based on the DFT. Since the DFT provides a discrete frequency representation of a finite duration sequence in the frequency domain, it is interesting to explore its use as a computational tool for linear system analysis and especially for linear filtering. We have already established that a system with frequency response h of w, when excited with an input signal that has a spectrum x of w, possesses an output spectrum y of w equal to x of w into h of w. The output sequence y of n is determined from its spectrum via the inverse Fourier transform. Computationally, the problem with this frequency domain approach is that x of omega, h of omega and y of omega are functions of the continuous variable omega. As a sequence, the computations cannot be done on a digital computer since the computer can only store and perform computations on quantities at discrete frequencies. On the other hand, the DFT does lend itself to computation on a digital computer. We present a computational procedure that serves as an alternative to time domain convolution. In fact, the frequency domain approach based on the DFT is computationally more efficient than time domain convolution due to the existence of efficient algorithms for computing the DFT. Use of the DFT in linear filtering. Circular convolution is of no use to us if our objective is to determine the output of a linear filter to a given input sequence. In this case, we seek a frequency domain methodology equivalent to linear convolution. Suppose that we have a finite duration sequence x of n of length L which excites an FIR filter of length m without loss of generality. Let x of n equal to 0 where n less than 0 and n greater than or equal to L, h of n equal to 0 where n less than 0 and n greater than or equal to m, where h of n is the impulse response of the FIR filter. The output sequence y of n of the FIR filter can be expressed in the time domain as the convolution of x of n and h of n, that is y of n equal to summation k equal to 0 to m minus 1 h of k into x of n minus k. Since h of n and x of n are finite duration sequences, their convolution is also finite in duration. In fact, the duration of y of n is L plus m minus 1. The frequency domain equivalent is y of omega equal to x of omega into h of omega. If the sequence y of n is to be represented uniquely in the frequency domain by samples of its spectrum y of omega at a set of discrete frequencies, the number of distinct samples must equal or exceed L plus m minus 1. Therefore, a DFT of size n greater than or equal to L plus m minus 1 is required to represent y of n in the frequency domain. Now, if y of k equivalents to y of k at omega equal to 2 pi k by n for k equal to 0, 1 etc. up to n minus 1 equal to x of omega into h of omega at omega equal to 2 pi k by n where k equal to 0, 1 etc. up to n minus 1, then y of k equal to x of k into h of k where k equal to 0, 1 etc. up to n minus 1, where x of k and h of k are the endpoint DFTs of the corresponding sequences x of n and h of n respectively. Since the sequences x of n and h of n have a duration less than n, we simply pad these sequences with the zeros to increase their length to n. This increase in the size of the sequences does not alter their spectra x of omega and h of omega, which are continuous spectra since the sequences are aperiodic. However, by sampling the spectra at n equally spaced points in frequency, computing the n-point DFTs, we have increased the number of samples that represent these sequences in the frequency domain beyond the minimum number L or M respectively. Since the n equal to L plus M minus 1 point DFT of the output sequence y of n is sufficient to represent y of n in the frequency domain, it follows that the multiplication of the n-point DFTs x of k and h of k followed by the computation the n-point circular convolution of x of n with h of n, that is, increase the length of the sequences x of n and h of n to n points by appending zeros. Circularly convolve the resulting sequences, we obtain the same result as would have been obtained with their linear convolution. Thus, with zero padding, the DFT can be used to perform linear filtering. Example, by means of the DFT and IDFT, determine the response of the FIR filter with impulse response h of n equal to 1, 2, 3 to the input sequence x of n equal to 1, 2, 2, 1. Solution. The input sequence has length L equal to 4 and the impulse response has length M equal to 3. Linear convolution of these two sequences produces a sequence of length n equal to 6. Consequently, the size of the DFTs must be at least 6. For simplicity, we compute 8-point DFTs x of k equal to summation n equal to 0 to 7 x of n into e power minus j 2 pi kn by n equal to 1 plus 2 into e power minus j pi k by 4 plus 2 into e power minus j pi k by 2 plus e power minus j 3 pi k by 4 where k equal to 0, 1 etc. up to 7. The computation yields x of 0 equal to 6, x of 1 equal to 2 plus root 2 by 2 minus j of 4 plus 3 root 2 by 2. X of 2 equal to minus 1 minus j, x of 3 equal to 2 minus root 2 by 2 plus j of 4 minus 3 root 2 by 2. X of 4 equal to 0, x of 5 equal to 2 minus root 2 by 2 minus j of 4 minus 3 root 2 by 2. X of 6 equal to minus 1 plus j, x of 7 equal to 2 plus root 2 divided by 2 plus j of 4 plus root 3 root 2 by 2. The 8-point DFT of h of n is h of k equal to summation n equal to 0 to 7 h of n into e power minus j 2 pi kn by 8 equal to 1 plus 2 into e power minus j pi k by 4 plus 3 into e power minus j pi k by 2. Hence h of 0 equal to 6, h of 1 equal to 1 plus root 2 minus j of 3 plus root 2, h of 2 equal to minus 2 minus j2, h of 3 equal to 1 minus root 2 plus j of 3 minus root 2, h of 4 equal to 2, h of 5 equal to 1 minus root 2 minus j of 3 minus root 2, h of 6 equal to minus 2 plus j2, h of 7 equal to 1 plus root 2 plus j of 3 plus root 2. The product of these two DFTs yields y of k, which is y of 0 equal to 36, y of 1 equal to minus 14.07 minus j 17.48, y of 2 equal to j4, y of 3 equal to 0.07 plus j into 0.515. Y of 4 equal to 0, y of 5 equal to 0.07 minus j into 0.515, y of 6 equal to minus j4, y of 7 equal to minus 14.07 plus j into 17.48. Finally, the 8-point IDFT is y of n equal to summation k equal to 0 to 7, y of k into e power j 2 pi kn by n, where n equal to 0, 1 etc. up to 7. This computation yields the result y of n equal to 1, 4, 9, 11, 8, 3, 0, 0. The first 6 values of y of n constitute the set of desired output values and the last 2 values are 0 because we used an 8-point DFT and IDFT. The multiplication of two DFTs corresponds to circular convolution in the time domain. H of n equal to 1, 2, 3, 0, 0, 0. X of n equal to 1, 2, 2, 1, 0, 0. Results in the output sequence. Y of n equal to 1, 4, 9, 11, 8, 3. Filtering of long data sequences. In practical applications involving linear filtering of signals, the input sequence x of n is often a very long sequence. Since Linear filtering performed via the DFT involves operations on a block of data. A long input signal sequence must be segmented to fixed size blocks. Prior processing. Since the filtering is linear, successive blocks can be processed one at a time via the DFT, and the output blocks are fitted together to form the overall output signal sequence. The input sequence is segmented into blocks and each block is processed via the DFT and IDFT to produce a block of output data. The output blocks are fitted together to form an overall output sequence which is identical to the sequence obtained if the long block had been processed via time domain convolution. The two methods are called the overlap save method and the overlap add method. For both methods, we assume that the FIR filter has duration m. The input data sequence is segmented into blocks of L points whereby assumption L greater than m without loss of generality. Overlap save method. In this method, the size of the input data blocks is n equal to L plus m minus 1 and the size of the DFTs and IDFTs are of length n. Each data block consists of the last m-1 data points of the previous data block followed by L new data points to form a data sequence of length n equal to L plus m minus 1. An n-point DFT is computed. For each data block, the impulse response of the FIR filter is increased in length by appending L-1 zeros and an n-point DFT of the sequence is computed once and stored. The multiplication of the two n-point DFTs h of k and x m of k for the mth block of data yields y cap m of k equal to h of k into x m of k, where k equal to 0, 1, etc. n minus 1. Then the n-point IDFT yields the result y cap m of n equal to y cap m of 0 into y cap n of 1, etc. y cap m of m minus 1, y cap n of m, etc. y cap m of n minus 1. Since the data record is of length n, the first m minus 1 points of ym of n are corrupted by aliasing must be discarded. The last L point of ym of n are exactly the same as the result from linear convolution, and as a consequence y cap m of n equal to y m of n into n equal to m into m plus 1 etc. n minus 1. To avoid loss of data due to aliasing, the last m minus 1 points of each data record are saved and these points become the first m minus 1 data points of the subsequent record. The first m minus 1 points of the first record are set to 0. Thus the blocks of data sequences are x1 of n equal to 0, 0, etc. 0 are called m minus 1 points, x of 0, x of 1, etc. x of L minus 1. x2 of n equal to x of L minus m plus 1, etc. x of L minus 1 are called m minus 1 data points from x1 of n. x of L, etc. x of 2L minus 1 are called L new data points. x3 of n equal to x of 2L minus m plus 1, etc. x of 2L minus L are called m minus 1 data points from x2 of n. x of 2L, etc. x of 3L minus 1 are called L new data points, and so forth. In the resulting data sequences from the IDFT, the first m minus 1 points are discarded due to the aliasing and the remaining L points constitute the desired result from linear convolution. Overlap add method. In this method, the size of the input data block is L points and the size of the DFTs and IDFT is n equal to L plus m minus 1. To each data block, we append m minus 1 zeros and compute the n point DFT. Thus, the data blocks may be represented as x1 of n equal to x of 0, x of 1, etc. x of L minus 1, 0, 0, etc. 0 or m minus 1 zeros. x2 of n equal to x of L, x of L plus 1, etc. x of 2L minus 1, 0, 0, etc. 0 are called m minus 1 zeros. x3 of n equal to x of 2l, etc. x of 3l minus 1, 0, 0, etc. 0 are called m minus 1 zeros, and so on. The two n-point DFTs are multiplied together to form ym of k equal to h of k into xm of k, where k equal to 0, 1, etc. n minus 1. The IDFT yields data blocks of length n that are free of aliasing, since the size of the DFTs and IDFT is n equal to l plus m minus 1, and the sequences are increased to n points by appending zeros to each block. Since each data block is terminated with m minus 1 zeros, the last m minus 1 points from each output block must be overlapped and added to the first m minus 1 points of the succeeding block. Hence, this method is called the overlap add method. This overlapping and adding yields the output sequence y of n equal to y1 of 0, y1 of 1, etc. y1 of l minus 1, y1 of l plus y2 of 0, y1 of l plus 1 plus y2 of 1, etc. y1 of n minus l plus y2 of m minus 1, y2 of m, etc. Linear FER filtering by the overlap add method. Properties of the DFT. In this section, we present the important properties of the DFT in view of the relationships established between the DFT and Fourier series and Fourier transforms and Z transforms of discrete time signals. We expect the properties of the DFT to resemble the properties of these transforms and series. However, some important difference exists, one of which is the circular convolution property derived in the following section. A good understanding of these properties is extremely helpful in the application of the DFT to practical problems. The notation used below to denote the n-point DFT pair x of n and x of k is x of n under DFT x of k. The DFT and inverse DFT IDFT for an n-point sequence x of n are given as DFT x of k equal to summation equal to 0 to n minus 1 x of n into wn or kn, where k equal to 0, 1, etc. up to n minus 1. IDFT x of n equal to 1 by n into summation k equal to 0 to n minus 1 x of k into wn power minus kn, where n equal to 0, 1, etc. up to n minus 1, where wn is defined as wn equal to e power minus j 2 pi by n. Periodicity, linearity and symmetry properties. Periodicity. If x of n and x of k are an n-point DFT pair, x of n plus n equal to x of n for all n, x of k plus n equal to x of k for all k. The periodicity property in the sequence x of n for a given DFT. Linearity. If x1 of n under DFT, x1 of k and x2 of n under DFT gives x2 of k, then for any real valued or complex valued constants a1 and a2, a1 into x1 of n plus a2 into x2 of n under DFT, a1 into x1 of k plus a2 into x2 of k. This property follows immediately from the definition of the DFT. Circular symmetries of a sequence. The n-point DFT of a finite duration sequence x of n of length L less than or equal to n is equivalent to the n-point DFT of a periodic sequence xp of n of period n, which is obtained by periodically xp of n equal to summation L equal to minus infinity to plus infinity x of n minus Ln. Now suppose that we shift the periodic sequence xp of n by k units to the right. Thus we obtain another periodic sequence xp dash of n equal to xp of n minus k equal to summation L equal to minus infinity to plus infinity x of n minus k minus Ln. the finite duration sequence x dash of n equal to xp dash of n, where 0 less than or equal to n less than or equal to n minus 1 and 0 otherwise. It is related to the original sequence x of n by a circular shift. In general, the circular shift of the sequence can be represented as the index modulo n. Thus, we can write x dash of n equal to x of n minus k comma modulo n, x of n minus k of n. For example, if k equal to 2 and n equal to 4, we have x dash of n equal to x of n minus 2 of 4, which implies that x dash of 0 equal to x of minus 2 of 4 equal to x of 2, x of 1 equal to x of minus 1 of 4 equal to x of 3, x dash of 2 equal to x of 0 of 4 equal to x of 0, x dash of 3 equal to x of 1 of 4 equal to x of 1. Hence, x dash of n is simply x of n shifted circular by 2 units in time. A circular shift of an n-point sequence is equivalent to a linear shift of its periodic extension and vice versa. An n-point sequence is called circularly even if it is symmetry about the point 0 on the circle. This implies that x of n minus n equal to x of n for 1 less than or equal to n less than or equal to n minus 1. An n-point sequence is called circularly add if it is antisymmetric about the point 0 on the circle. This implies that x of n minus n equal to minus x of n for 1 less than or equal to n less than or equal to n minus 1. The time reversal of an n-point sequence is attained by reversing its samples about the point 0 on the circle. Thus, the sequence x of minus n of n is simply given as x of minus n of n equal to x of n minus n for 0 less than or equal to n less than or equal to n minus 1. This time reversal is equidistant by plotting x of n in a clockwise direction on a circle. An equivalent definition of even and odd sequences for the associated periodic sequence xp of n is given as follows. Even xp of n equal to xp of minus n equal to xp of n minus n. Odd xp of n equal to minus xp of minus n equal to minus xp of n minus n. If the periodic sequence is complex valued, we have conjugate even xp of n equal to xp star of n minus n, conjugate odd xp of n equal to minus xp star of n minus n. These relationships suggest that we decompose the sequence xp of n as xp of n equal to xp of n plus xp naught of n, where xp of n equal to 1 by 2 into xp of n plus xp star of n minus n, xp naught of n equal to 1 by 2 times of xp of n minus xp star of n minus n. Symmetry properties of the DFT. The symmetry properties for the DFT can be obtained by applying the methodology previously used for the Fourier transform. Let us assume that the n-point sequence x of n and its DFT are both complex valued. Then the sequences can be expressed as x of n equal to xr of n plus j into xj of n, where 0 less than or equal to n less than or equal to n minus 1. X of k equal to xr of k plus j into xl of k, where 0 less than or equal to k less than or equal to n minus 1. By substituting x of n into the expression for the DFT, we obtain xr of k equal to summation n equal to 0 to n minus 1 xr of n into cos 2 pi kn by n plus xl of n into sin 2 pi kn by n, xl of k equal to minus summation n equal to 0 to n minus 1 xr of n into sin of 2 pi kn by n minus xl of n into cos of 2 pi kn by n. Similarly, by substituting x of k into the expression for the IDFT, we obtain xr of n equal to 1 by n summation k equal to 0 to n minus 1 xr of k into cos 2 pi kn by n minus x1 of k into sin 2 pi kn by n. xl of n equal to 1 by n into summation k equal to 0 to n minus 1 x r of k into sin 2 pi kn by n plus xl of k into cos 2 pi kn by n. Real valued sequences. If the sequence is x of n is real, it follows directly from DFT formula that x of n minus k equal to x star of k equal to x of minus k. Consequently, modulus of x n minus k equal to modulus of x of k and Lx of n minus k equal to minus Lx of k. Furthermore, x1 of n equal to 0 and therefore x of n can be determined from below equation. xr of n equal to 1 by n into summation k equal to 0 to n minus 1 xr of k into cos 2 pi kn by n minus x1 of k into sin 2 pi kn by n. Real and even sequences. If x of n is real and even, that is x of n equal to x of n minus n for 0 less than or equal to n less than or equal to n minus 1, then below equation yields x1 of k equal to 0, xl of k equal to minus summation n equal to 0 to n minus 1 xr of pi into sin 2 pi kn by n minus xl of n into cos 2 pi kn by n. Hence, the DFT reduces to x of k equal to summation n equal to 0 to n minus 1 x of k into cos 2 pi kn by n, where 0 less than or equal to k less than or equal to n minus 1, which is itself real valued and even. Furthermore, since x1 of n equal to 0, the IDFT reduces to x of n equal to 1 by n summation k equal to 0 to n minus 1 x of k into cos 2 pi kn by n, where 0 less than or equal to n less than or equal to n minus 1. Real and odd sequences. If x of n is real and odd, that is x of n equal to minus x of n minus n for 0 less than or equal to n less than or equal to n minus 1, then below equation yields xr of k equal to 0, xr of k equal to summation n equal to 0 to n minus 1 xr of n into cos 2 pi kn by n plus xl of n into sin 2 pi kn by n. X of k equal to minus j summation n equal to 0 to n minus 1 x of n into sin 2 pi kn by n for 0 less than or equal to k less than or equal to n minus 1, which is purely imaginary and odd. Since xr of k equal to 0, the IDFT reduces to x of n equal to j into 1 by n into summation k equal to 0 to n minus 1 x of k into sin 2 pi kn by n, where 0 less than or equal to n less than or equal to n minus 1. Purely imaginary sequences. In the sequence x of n equal to j into x1 of n, consequently below equation x r of k equal to summation n equal to 0 to n minus 1 x r of n into cos 2 pi kn by n plus xl of n into sin 2 pi kn by n. xl of n equal to minus summation n equal to 0 to n minus 1 xr of n into sin 2 pi kn by n minus xl of n into cos 2 pi kn by n reduces to xr of k equal to summation n equal to 0 to n minus 1 xl of n into sin 2 pi kn by n. xl of k equal to summation n equal to 0 to n minus 1 xl of n into cos 2 pi kn by n. We observe that xr of k is odd and x1 of k is even. If x1 of n is odd, then x1 of k equal to 0 and hence x of k is purely real. On the other hand, if x1 of n is even, then xr of k equal to 0 and hence x of k is purely imaginary. The symmetry properties given above may be summarized as follows. X of n equal to x r power e of n plus x r power 0 of r plus j into x l power e of n plus j into x l power 0 of n, etc. X of k equal to x r power e of k plus x r power 0 of k plus j into x l power e of k plus j into x l power 0 of k. For example, the DFT of the sequence xp of n equal to 1 by 2 into xp of n plus xp star of n minus n is xr of k equal to x r power e of k plus x r power 0 of k. We can see in the table n point sequence x of n for 0 less than or equal to n less than or equal to n minus 1 and n point DFT. Multiplication of two DFTs and circular convolution. Suppose that we have two finite duration sequences of length n, x1 of n and x2 of n. The respective n point DFTs are x1 of k equal to summation n equal to 0 to n minus 1 x1 of n into e power minus j 2 pi nk by n, where k equal to 0, 1 etc. n minus 1. x2 of k equal to summation n equal to 0 to n minus 1 x2 of n into e power minus j 2 pi nk by n, where k equal to 0, 1 etc. n minus 1. If we multiply the two DFTs together, the result is a DFT, say x3 of k of a sequence x3 of n of length n. Let us determine the relationship between x3 of n and the sequences x1 of n and x2 of n. We have x3 of k equal to x1 of k into x2 of k, where k equal to 0, 1 etc. n minus 1. The IDFT of x3 of k is x3 of m equal to 1 by n into summation k equal to 0 to n minus 1 x3 of k into e power j 2 pi km by n equal to 1 by n summation k equal to 0 to n minus 1 x1 of k into x2 of k into e power j 2 pi km by n. Suppose that we substitute for x1 of k and x2 of k in above equation. Thus we obtain x3 of n equal to summation k equal to 0 to n minus 1 into within the bracket summation n equal to 0 to n minus 1 x1 of n into e power minus j 2 pi kn by n into within the bracket summation n equal to 0 to n minus 1 x2 of l into e power minus j 2 pi kl by n into outside the bracket e power j 2 pi km by n equal to 1 by n summation n equal to 0 to n minus 1 x1 of n into summation l equal to 0 to n minus 1 x2 of l into within the bracket summation k equal to 0 to n minus 1 e power j 2 pi k of m minus n minus 1 divided by n. The inner sum in the brackets of above equation as the form summation k equal to 0 to n minus 1 a power k equal to n for a equal to 1 1 minus a power n divided by 1 minus a not equal to 1, where a is defined as a equal to e power j 2 pi of m minus n minus l divided by n. We observe that a equal to 1 when m minus n minus 1 is a multiple of n. On the other hand, a power n equal to 1 for any value of a not equal to 0. Consequently, summation k equal to 0 to n minus 1 a power k equal to n for l equal to m minus n plus pn equal to m minus n of n, where p an integer and a 0 otherwise. If we substitute above result into x3 of m, we obtain x3 of m equal to summation n equal to 0 to n minus 1 x1 of n into x2 of m minus n of n, where m equal to 0, 1 etc. up to n minus 1. The above expression has the form of a convolution sum. The convolution sum involves the index m minus n of n is called a circular convolution. Thus we conclude that multiplication of the DFTs of two sequences is equivalent to the circular convolution of the two sequences in the time domain. Example: perform the circular convolution of the following two sequences x1 of n equal to 2, 1, 2, 1. Then x2 of n equal to 1, 2, 3, 4. Solution. Each sequence consists of 4 non-zero points. Now x3 of m is obtained by circularly convolving x1 of n with x2 of n. Beginning with m equal to 0, we have x3 of 0 equal to summation n equal to 0 to 3 x1 of n into x2 of minus n of n. x2 of minus n of 4 is simply the sequence x2 of n folded and graphed on a circle. The product sequence is obtained by multiplying x1 of n with x2 of minus n of 4 point by point. Finally, we sum the values in the product sequence to obtain x3 of 0 equal to 14. For m equal to 1, we have x3 of 1 equal to summation n equal to 0 to 3 x1 of n into x2 of 1 minus n of 4. It is easily verified that x2 of 1 minus n of 4 is simply the sequence x2 of minus n of 4 rotated counterclockwise by 1 unit in time. This rotated sequence multiplies x1 of n to yield the product sequence. Finally, we sum the values in the product sequence to obtain x3 of 1. Thus, x3 of 1 equal to 16. For m equal to 2, we have x3 of 2 equal to summation n equal to 0 to 3 x1 of n into x2 of n minus n of 4. Now, x2 of 2 minus n of 4 is the folded sequence rotated 2 units of time in the counterclockwise direction. Along with the product sequence x1 of n, x2 of 2 minus n of 4, by summing the 4 terms in the product sequence we obtain x3 of 2 equal to 14. For m equal to 3, we have x3 of 3 equal to summation n equal to 0 to 3 x1 of n into x2 of 3 minus n of 4. The folded sequence x2 of minus n is now rotated by 3 units in time to yield x2 of 3 minus n of 4, and the resultant sequence is multiplied by x1 of n to yield the product sequence. The sum of the values in the product sequence is x3 of 3 equal to 16. The circular convolution of the two sequences x1 of n and x2 of n yields the sequence x3 of n equal to 14, 16, 14, 16. Circular convolution involves basically the same steps as the ordinary linear convolution: folding, time reversing one sequence, shifting the folded sequence, multiplying the product sequence. The basic difference between these two types of convolution is that in circular convolution, the folding and shifting rotating operations are performed in a circular fashion by computing the index of one of the sequences modulo n. In linear convolution, there is no modulo n operation. Either one of the two sequences may be folded and rotated without changing the result of the circular convolution. Thus, x3 of m equal to summation n equal to 0 to n minus 1 x2 of n into x1 of m minus n of n for m equal to 0, 1, etc. up to n minus 1. Example: by means of the DFT and IDFT, determine the sequence x3 of n corresponding to the circular convolution of the sequences x1 of n and x2 of n. x1 of n equal to 2, 1, 2, 1 and x2 of n equal to 1, 2, 3, 4. Solution: the 4-point DFT of x1 of n is x1 of k equal to summation n equal to 0 to 3 x1 of n into e power minus j 2 pi n k by 4, where k equal to 0, 1, 2, 3 equal to 2 plus e power minus j pi k by 2 plus 2 into e power minus j pi k plus e power minus j 3 pi k divided by 2. Thus x1 of 0 equal to 6, x1 of 1 equal to 0, x1 of 2 equal to 2, x1 of 3 equal to 0. The DFT of x2 of n is x2 of k equal to summation n equal to 0 to 3 x2 of n into e power minus j 2 pi nk by 4, where k equal to 0, 1, 2, 3 equal to 1 plus 2 times of e power minus j pi k by 2 plus 3 into e power minus j pi k plus 4 into e power minus j 3 pi k divided by 2. Thus x2 of 0 equal to 10, x2 of 1 equal to minus 2 plus j2, x2 of 2 equal to minus 2, x2 of 3 equal to minus 2 minus j2. When we multiply the two DFTs, we obtain the product x3 of k equal to x1 of k into x2 of k. Now the IDFT of x3 of k, x3 of n equal to summation k equal to 0 to 3 x3 of k into e power j 2 pi nk by 4, where n equal to 0, 1, 2, 3 equal to 1 by 4 into 60 minus 4 into e power j pi n. Thus x3 of 0 equal to 14, x3 of 1 equal to 16, x3 of 2 equal to 14, x3 of 3 equal to 16. Circular convolution. If x1 of n under DFT gives x1 of k and x2 of n under DFT gives x2 of k, then x1 of n circular convolution of x2 of n under DFT gives x1 of k into x2 of k, where x1 of n circular convolution of x2 of n denotes the circular convolution of the sequences x1 of n and x2 of n. Time reversal of a sequence. If x of n under DFT gives x of k, then x of minus n of n equal to x of n minus n under DFT gives x of minus k of n equal to x of n minus k. Hence reversing the n point sequence in time is equivalent to reversing the DFT values. Proof. From the definition of the DFT, we have DFT x of n minus n equal to summation n equal to 0 to n minus 1 x of n minus n into e power minus j 2 pi k n by n. If we change the index from n to m equal to n minus n, then DFT x of n minus n equal to summation m equal to 0 to n minus 1 x of m into e power minus j 2 pi k of n minus m by n equal to summation m equal to 0 to n minus 1 x of m into e power j 2 pi k m by n equal to summation m equal to 0 to n minus 1 x of m into e power minus j 2 pi n of n minus k by n equal to x of n minus k. We note that x of n minus k equal to x of minus k of n, where 0 less than or equal to k less than or equal to n minus 1. Circular time shift of a sequence. If x of n under DFT gives x of k, then x minus nl of n under DFT gives x of k into e power minus j 2 pi kl by n. Proof. From the definition of the DFT, we have DFT x of n minus l of n equal to summation n equal to 0 to n minus 1 x of n minus l of n into e power minus j 2 pi k n by n equal to summation n equal to 0 to l minus 1 x of n minus l of n into e power minus j 2 pi k n by n plus summation n equal to l to n minus 1 x of n minus l into e power minus j pi k n by n. But x of n minus 1 of n equal to x of n minus l plus n. Consequently, summation n equal to 0 to l minus 1 x of n minus l of n into e power minus j 2 pi kn by n equal to summation n equal to 0 to L minus 1 x of n minus L plus n into e power minus j 2 pi kn by n equal to summation m equal to n minus L to n minus 1 x of m into e power minus j 2 pi k of m plus L by n. Furthermore, summation n equal to L to n minus 1 x of n minus L into e power minus j 2 pi kn by n equal to summation m equal to 0 to n minus 1 minus L x of m into e power minus j 2 pi k of m plus L by n. Therefore, DFT x of n minus L equal to summation m equal to 0 to n minus 1 x of m into e power minus j 2 pi k of m plus L by n equal to x of k into e power minus j 2 pi k L by n. Circular frequency shift. If x of n under DFT x of k, then x of n into e power j 2 pi L n by n under DFT x k minus L of n. Hence, the multiplication of the sequence x of n with the complex exponential sequence e power j 2 pi k n by n is equivalent to the circular shift of the DFT by 1 units in frequency. This is the dual of the circular time shifting property. Complex conjugate properties. If x of n under DFT x of k, then x star of n under DFT x star of minus k of n equal to x star of n minus k. The proof of this property is left as an exercise for the reader. The IDFT of x star of k is 1 by n into summation k equal to 0 to n minus 1 x star of k into e power j 2 pi k n by n equal to 1 by n summation k equal to 0 to n minus 1 x of k into e power j 2 pi k of n minus n by n. Therefore, x star of minus n of n equal to x star of n minus n under DFT x star of k. Circular correlation. In general, for complex valued sequences x of n and y of n, if x of n under DFT x of k and y of n under DFT y of k, then r cap x y of L under DFT r cap x y of k equal to x of k into y star of k, where r x y of L is the unnormalized circular cross correlation sequence defined as r cap x y of L equal to summation n equal to 0 to n minus 1 x of n into y star of n minus L of n. Proof: we can write r x y of L as the circular convolution of x of n with the y star of minus n, that is r cap x y of L equal to x of L circular convolution y star of minus L. Then, with the aid of the properties in 5.2.41 and 5.2.46, the endpoint DFT of r x y of L is r x y of k equal to x of k into y star of k. In the special case where y of n equal to x of n, we have the corresponding expression for the circular autocorrelation of x of n. R cap xx of L under DFT R cap xx of k equal to modulus of x of k the whole square. Percival's theorem. For complex valued sequences x of n and y of n, in general, if x of n under DFT x of k and y of n under DFT y of k, then summation n equal to 0 to n minus 1 x of n into y star of n equal to 1 by n into summation k equal to 0 to n minus 1 x of k into y star of k. Proof: the property follows immediately from the circular correlation property. We have summation n equal to 0 to n minus 1 x of n into y star of n equal to r cap xy of 0 and r cap xy of L equal to 1 by n into summation k equal to 0 to n minus 1 r cap xy of k into e power j 2 pi k L by n equal to 1 by n into summation k equal to 0 to n minus 1 x of k into y star of k into e power j 2 pi k L by n. In the special case where y of n equal to x of n, summation n equal to 0 to n minus 1 modulus of x of n the whole square equal to 1 by n into summation k equal to 0 to n minus 1 modulus of x of k the whole square. Multiplication of two sequences. If x1 of n under DFT x1 of k and x2 of n under DFT x2 of k, then x1 of n into x2 of n under DFT 1 by n into x1 of k, circular convolution of x2 of k. Its proof follows simply by interchanging the rules of time and frequency in the expression for the circular convolution of two sequences. We can see in the table property, time domain and frequency domain. Quantization effects in the computation of the DFT. The DFT plays an important role in many digital signal processing applications, including FIR filtering, the computation of the correlation between signals, and spectral analysis. For this reason, it is important for us to know the effect of quantization errors in its computation. In particular, we shall consider the effect of quantization errors due to the multiplications performed in the DFT with fixed point arithmetic. The model that we shall adopt for characterizing round-off errors in multiplication is the additive white noise model that we use in the statistical analysis of round-off errors in IIR and FIR filters. Although the statistical analysis is performed for rounding, the analysis can be easily modified to apply to truncation in 2's complement arithmetic. Of particular interest is the analysis of round-off errors in the computation of the DFT via the FFT algorithm. However, we shall first establish a benchmark by determining the round-off errors in the direct computation of the DFT. Quantization errors in the direct computation of DFT. Given a finite duration sequence x of n 0 less than or equal to n less than or equal to n minus 1, the DFT of x of n is defined as x of k equal to summation n equal to 0 to n minus 1 x of n into wn power kn, where k equal to 0, 1 etc. n minus 1, where wn equal to e power minus j 2 pi by n. We assume that in general x of n is a complex valued sequence. We also assume that the real and imaginary components of x of n and wn power kn are represented by b bits. Consequently, the computation of the product x of n into wn power kn requires 4 real multiplications. Each real multiplication is rounded from 2b bits to b bits, and hence there are 4 quantization errors for each complex valued multiplication. In the direct computation of the DFT, there are n complex valued multiplications for each point in the DFT. Therefore, the total number of real multiplications in the computation of a single point in the DFT is 4n. Consequently, there are 4n quantization errors. Let us evaluate the variance of the quantization errors in a fixed point computation of the DFT. First, we make the following assumptions about the statistical properties of the quantization errors. Number 1. The quantization errors due to rounding are uniformly distributed random variables in the range minus delta by 2, delta by 2, where delta equal to 2 power minus h. Number 2. The Fourier quantization errors are mutually uncorrelated. Number 3. The Fourier quantization errors are uncorrelated with the sequence x of n. Since each of the quantization errors has a variance sigma r square equal to delta square by 12 equal to 2 power minus 2b divided by 12. The variance of the quantization errors from the Fourier multiplication is sigma q square equal to 4n sigma e square equal to n by 3 into 2 power minus 2b. Hence, the variance of the quantization error is proportional to the size of DFT. Note that when n is a power of 2, the variance can be expressed as sigma q square equal to 2 power minus 2 of b minus b by 2 divided by 3. This expression implies that every fourfold increase in the size n of the DFT requires an additional bit in computational precision to offset the additional quantization errors. To prevent overflow, the input sequence to the DFT requires scaling. Clearly, an upper bound on modulus of x of k is modulus of x of k less than or equal to summation n equal to 0 to n minus 1 modulus of x of n. if the dynamic range in addition is -1, 1, then modulus of x of k less than 1 requires that summation n equal to 0 to n minus 1, modulus of x of n less than 1. If modulus of x of n is initially scaled such that modulus of x of n less than 1 for all n, then each point in the sequence can be divided by n. The scaling implied is extremely severe. For example, suppose that the signal sequence x of n is wide and after scaling, each value modulus of x of n of the sequence is uniformly distributed in the range -1 by n, 1 by n. Then the variance of the signal sequences sigma x square equal to 2 by n the whole square divided by 12 equal to 1 by 3n square. And the variance of the output DFT coefficients modulus of x of k is sigma x square equal to n into sigma x square equal to 1 by 3n. Thus the signal to noise power ratio is sigma x square by sigma q square equal to 2 power 2b divided by n square. We observe that the scaling is responsible for reducing the SNR by n, and the combination of scaling and quantization errors result in a total reduction that is proportional to n square. Hence, scaling the input sequence x of n imposes a severe penalty on the signal to noise ratio in the DFT. Example: use below equation to determine the number of bits required to compute the DFT of a 1024 point sequence with a SNR of 30 dp. Sigma x square by sigma q square equal to 2 power 2b divided by n square. Solution: the size of the sequence is n equal to 2 power 10. Hence the SNR is 10 into log base 10 sigma x square by sigma q square equal to 10 into log base 10 2 power 2b minus 20. For an SNR of 30 dp, we have 3 times of 2b minus 20 equal to 30, b equal to 15 bits. Note that the 15 bits is the precision for both multiplication and addition. Instead of scaling the input sequence x of n, suppose we simply require that modulus of x of n less than 1, then we must provide a sufficiently large dynamic range for addition such that modulus of x of k less than n. In such a case, the variance of the sequence modulus of x of n is sigma x square equal to 1 by 3, and hence the variance of modulus of x of k is sigma x square equal to n into sigma x square equal to n by 3. Consequently, the SNR is sigma x square by sigma q square equal to 2 power 2b. If we repeat the computation, we find that the number of bits required to achieve a SNR of 30 dp is b equal to 5 bits. However, we need an additional 10 bits for the accumulator, the adder, to accommodate the increase in the dynamic range for addition. Although we did not achieve any reduction in the dynamic range for addition, we have managed to reduce the precision in multiplication from 15 bits to 5 bits, which is highly significant. Quantization errors in FFT algorithms. The FFT algorithms require significantly fewer multiplications than the direct computation of the DFT. The computation of the DFT via an FFT algorithm will result in smaller quantization errors. Unfortunately, that is not the case, as we will demonstrate. Let us consider the use of fixed point arithmetic in the computation of a radix 2 FFT algorithm. To be specific, we select the radix 2 decimation in time algorithm for the k is n equal to 8. The results on quantization errors that we obtain for this radix 2 FFT algorithm are typical of the results obtained with other radix 2 and higher radix algorithms. We observe that each butterfly computation involves one complex valued multiplication or equivalently 4 real multiplications. We ignore the fact that some butterflies contain a trivial multiplication by plus or minus 1. If we consider the butterflies that affect the computation of any one value of the DFT, we find that in general there are n by 2 in the first stage of the FFT n by 4 in the second stage, n by 8 in the third stage, and so on until the last stage where there is only one. Consequently, the number of butterflies per output point is 2 power v minus 1 plus 2 power v minus 2 plus etc. 2 plus 1 equal to 2 power v minus 1 of 1 plus 1 by 2 plus etc. plus 1 by 2 whole power v minus 1 equal to 2 power v into 1 minus 1 by 2 whole power v equal to n minus 1. Figure decimation in time FFT algorithm. The quantization errors introduced in each butterfly propagate to the output. The quantization errors introduced in the first stage propagate through v minus 1 stages. Those introduced in the second stage propagate through v minus 2 stages, and so on. As these quantization errors propagate through a number of subsequent stages, they are phase shifted, phase rotated by the phase factors Wn power kn. These phase rotations do not change the statistical properties of the quantization errors, and in particular, the variance of each quantization error remains invariant. If we assume that the quantization errors in each butterfly are uncorrelated with the errors in other butterflies, then there are 4 times of n minus 1 errors that affect the output of each point of the FFT. Consequently, the variance of the total quantization error at the output is sigma q square equal to 4 times of n minus 1 into delta square by 12, approximately equal to n delta square by 3, where delta equal to 2 power minus b. Hence, delta q square equal to n by 3 into 2 power minus 2b. This is exactly the same result that we obtained for the direct computation of the DFT. As in the case of the direct computation of the DFT, we must scale the input sequence to prevent overflow. If modulus of x of n less than 1 by n, 0 less than or equal to n less than or equal to n minus 1, then modulus of x of k less than 1 for 0 less than or equal to k less than or equal to n minus 1. Thus, overflow is avoided. Since the FFT algorithm consists of a sequence of stages where each stage contains butterflies that involve pairs of points, it is possible to devise a different scaling strategy that is not as severe as dividing each input point by n. This alternative scaling strategy is motivated by the observation that the intermediate values xn of k, the n equal to 1 to etc. v stages of the FFT algorithm satisfy the conditions. Maximum of modulus of x of n plus 1 of k, x of n plus 1 of l greater than or equal to maximum of modulus of xn of k, modulus of xn of l. Maximum of xn plus 1 of k, xn plus 1 of l less than or equal to 2 times of maximum of modulus of xn of k into modulus of xn of l. If modulus of x of n less than 1, we apply a scale factor of 1 by 2 in the first stage, so that modulus of x of n less than 1 by 2. Then the output of each subsequent stage in the FFT algorithm is scaled by 1 by 2. So that v stages we have achieved an overall scale factor of 1 by 2 whole power v equal to 1 by n. Thus, overflow in the computation of the DFT is avoided. The scaling procedure does not affect the signal level at the output of the FFT algorithm, but it significantly reduces the variance of the quantization errors at the output. Specifically, each factor of 1 by 2 reduces the variance of a quantization error term by a factor of 1 by 4. Thus, the 4 times of n by 2 quantization errors introduced in the first stage are reduced in variance 1 by 4 whole power v minus 1. The 4 times of n by 4 quantization errors introduced in the second stage are reduced in variance by 1 by 4 whole power v minus 2, and so on. The total variance of the quantization errors at the output of the FFT algorithm is sigma q square equal to delta square by 12 of 4 into n by 2 into 1 by 4 whole power v minus 1 plus 4 into n by 4 into 1 by 4 whole power v minus 2 plus 4 into n by 8 into 1 by 4 whole power v minus 3 plus etc. plus 4 equal to delta square by 3 into 1 by 2 whole power v minus 1 plus 1 by 2 whole power v minus 2 plus etc. plus 1 by 2 plus 1 equal to 2 delta square by 3 into 1 minus 1 by 2 whole power v approximately equal to 2 by 3 into 2 power minus 2b, where the factor 1 by 2 whole power v is negligible. The signal has the variance sigma x square equal to 1 by 3n, hence the SNR is sigma x square by sigma q square equal to 1 by 2n into 2 power 2b equal to 2 power 2b minus b minus 1. Thus, by distributing the scaling of 1 by n uniformly throughout the FFT algorithm, we have achieved as SNR that is inversely proportional to instead of n square. Figure butterflies that affect the computation of x of 3. The Godsell algorithm. The Godsell algorithm exploits the periodicity of the phase factors Wn power k and allows us to express the computation of the DFT as a linear filtering operation. Since Wn power minus kn equal to 1, we can multiply the DFT by this factor. Thus, x of k equal to Wn power minus kn into summation m equal to 0 to n minus 1, x of m into Wn power km equal to summation m equal to 0 to n minus 1, x of m into Wn power minus k of n minus m. We note that the above equation is in the form of a convolution. Indeed, if we define the sequence yk of n as yk of n equal to summation m equal to 0 to n minus 1, x of m into Wn power minus k of n minus m, then it is clear that yk of n is the convolution of the finite duration input sequence x of n of length n with the filter as an impulse response hk of n equal to Wn power minus kn into u of n. The output of this filter at n equal to n yields the value of the DFT at the frequency omega k equal to 2 pi k by n, that is x of k equal to yk of n at n equal to n. The filter with the impulse response hk of n as the system function hk of z equal to 1 divided by 1 minus Wn power minus k into z power minus 1. This filter has a pole on the unit circle at the frequency omega k equal to 2 pi k divided by n. Thus, the entire DFT can be computed by passing the block of input data into a parallel bank of n single pole filters, where each filter has a pole at the corresponding frequency of the DFT. Instead of performing the computation of the DFT via convolution, we can use the difference equation to compute yk of n recursively. Thus, we have yk of n equal to Wn power minus k, yk of n minus 1 plus x of n, yk of minus 1 equal to 0. The desired output is x of k equal to yk of n for k equal to 0, 1, etc. n minus 1. To perform this computation, we can compute once and store the phase factors Wn power minus k. The complex multiplications and additions can be avoided by combining the pairs of resonators possessing complex conjugate poles. This leads to two-pole filters with system functions of the form hk of z equal to 1 minus Wn power k into z power minus 1 divided by 1 minus 2 into cos of 2 pi k by n into z power minus 1 plus z power minus 2. The direct form to realization of the system is described by the difference equation. Vk of n equal to 2 times of cos 2 pi k by n into Vk of n minus 1 minus Vk of n minus 2 plus x of n. Yk of n equal to Vk of n minus Wn power k into Vk of n minus 1 with initial conditions Vk of minus 1 equal to Vk of minus 2 equal to 0. The recursive relation is iterated for n equal to 0, 1, etc. up to n, but the above equation is computed only once at time n equal to n. Each iteration requires one real multiplication and two additions. Consequently, for a real input sequence x of n, this algorithm requires n plus 1 real multiplications to yield not only x of k but also, due to symmetry, the value of x of n minus k. The goat cell algorithm is particularly attractive when the DFT is to be computed at a relatively small number m of values, where m less than or equal to log 2n. Otherwise, the FFT algorithm is a more efficient method. Figure. Direct form to realization of two-pole resonator of computing the DFT. Conclusion. In this chapter, we have covered the following in detail: frequency domain sampling, properties of DFT, linear filtering method based on DFT, frequency analysis of signals using DFT, FFT algorithm, applications of FFT, goat cell algorithm, quantization effects in the computation of DFT.